Okay, so let's start a new section, inverse functions and derivatives. The main concern here is this. Suppose you have a function f with domain x and range y, where both f, x and y are subsets of the set of real numbers. Now there are two conditions on this function. It is differentiable and invertible. Let us not take the word differentiable too seriously, in the sense that we are not saying if the function f is differentiable at every point in x or at some points in x. It is differentiable somewhere in x, but it's also invertible. Now, as an invertible function, it will have an inverse, which is a function from y into x. Now the question is this: does differentiability of f imply f inverse is also differentiable at some points? If so, can we say what the derivative of f inverse is at that point in terms of the derivatives of f? So we are going to investigate these things in this section. And we start with this lemma. Lemma also starts accordingly. We have a function f from x into y, which is an invertible function where x and y are subsets of R. And we are taking 2 points, one point x naught in x in the domain of f and one point y naught in y in the range of f, so that y naught is nothing but the image of x naught under f. Y is f of x naught. Now we state the differentiability conditions more precisely. It is given that f is differentiable at x naught and f inverse is differentiable at y naught. Then the derivative of f inverse at y naught is the reciprocal of the derivative of f at x naught. Let us see how the conditions look symbolically. You see, it makes sense to say that f is differentiable at x naught because x naught is a point in the domain of f. And it also similarly makes sense to say that f inverse is differentiable at y naught because y naught is a point in capital Y, which is the domain of f inverse. Then those two derivatives, the derivative of f at x naught and the derivative of f inverse at y naught, are related by this equation. Okay, so let us now see the proof. The proof is going to start by applying the chain rule. And that's why before starting to write the proof, let us see the statement of chain rule for once, like this. Of course, such explanations or elaborations need not be part of a proof. Okay, what I am trying to say here is that do not write a proof like this. This is only for our understanding that we are writing like this. What does the chain rule say? In the chain rule, we have two functions. One of the functions is just like our f, where x and y are subsets of R. And there is another function g from y into R. Okay. Now, say x naught is a point in x. Now, two conditions are given. about differentiability of f and g. F is differentiable at x naught, like what we have here, and g is differentiable at f of x naught. Does that make sense? Yes, because f of x naught is an element in y. So g can be differentiable at an element in y. Then the conclusion of the chain rule is that then the composition G composition f is also differentiable at x naught, because the domain of G composition f is x and range, of course, you can take R. But the main part of the chain rule is that equation which relates the derivatives. And that equation is, of course, this. The derivative of G composition f at x naught is equal to the derivative of G at f of x naught times the derivative of f at x naught. Alright, so this is our chain rule. Now we want to use the chain rule here in our present situation. So we have our function f in chain rule. We have f, here also we have f, that's same f, okay, we are taking. However, what shall we take in place of g? In place of g, we are going to take f inverse, and actually not the exact function f inverse, but a slightly different one. We have changed the range of f inverse from x into R in order to apply the chain rule. This doesn't significantly affect anything actually, because all the f inverse images are inside x, so automatically they are also inside R because x is a subset of R. You cannot change the range of a function like this if, for example, in situations like this, where you are interested in showing that the function is a bijection or is surjective. In such cases, you cannot change the range. But right now we can, because we are more interested in the values of f inverse than what the range of the function f inverse is. Alright. Now, are the hypotheses matching here? F is differentiable at a point x naught in x. Here also f is differentiable at a point x naught in x. Now, f inverse, in place of f inverse, here we have g. G is differentiable at f of x naught. If you go back to the statement of this lemma, for us the f of x naught is y naught, and it is given that f inverse is differentiable at y naught. That means we are able to apply the chain rule with these two things. And the conclusion of the chain rule will be that G composition f is differentiable at x naught, and let's see what this equation becomes. F inverse composition f has derivative at x naught, which is equal to the derivative of f inverse, that is g prime, of f of x naught times the derivative of f at x naught. But because this is y naught, so f inverse prime y naught times f prime x naught. Okay, so this is how we are going to apply the chain rule. But of course, these sort of things are really not that difficult, and that is why they are not shown in a proof. Very often, if it is not really that difficult, it's straightforward application of some known rule, we just write like this. So that this is how the proof starts, by the chain rule, which in this text is theorem, so that if you want to see the actual statement, you can go and see this theorem. We straight away write times f prime of x naught. This much we are supposed to figure out ourselves. But we are not quite there yet, although we have got these two quantities. One of them is this and we have this. But still, we have to say something about the left hand side here. The left hand side is the derivative of f inverse composition f at x naught. Now we know what f inverse composition f is. It is the identity function on the set X. Since f inverse composition f is the identity function on X. If you find this notation unrecognizable, you recall that we have actually seen this in an exercise long ago. And that exercise is 338. In the third chapter, we have seen this while going through sets and functions, those things. Okay. Now, in the first section of this chapter on differentiation, we have seen that when you differentiate an identity function at any point in its domain, you get 1. That's why the derivative of this at x naught, which is just the derivative of this at x naught, is 1. So that means this becomes 1 now. Can you now see why this is not 0? Yes, because if it is 0, the right hand side would be 0, whereas the left hand side is 1. This, in particular, implies that this is not equal to 0. And that is why we can divide both sides by this derivative. Thus, and have our claim. So that is the proof of this lemma. Now, as nice as the lemma is, it has a shortcoming. Let's now come to that. You do one thing, you go back to the statement of the lemma and see the hypothesis carefully. The lemma, what are the ingredients here? You have a function f from x into y, which is invertible and is differentiable at a point x naught in its domain. Being invertible, the function f has an inverse, f inverse. and f inverse is differentiable at y naught, and y naught is f of x naught. And then the conclusion is that the derivatives are related by this equation. So that means this lemma actually is not telling you as a conclusion that f inverse is differentiable. In fact, differentiability of f inverse is a hypothesis, it's not a conclusion. So it gives you two things. You need two things in order to be able to apply this lemma. F should be differentiable, f inverse also should be differentiable. Then the lemma just tells you how the derivatives are related. We want to be able to say that f inverse is differentiable as a conclusion. Okay, so we need to improve this lemma. But before we go to the main result, there are some things to consider here. Alright, one of the things is this condition itself. What happens if you get this condition? This condition means its negation. Say you encounter a function which is differentiable at x naught, but there the derivative is 0. Will the lemma fail? Yes, there are examples where the lemma fails. One such example is this. Consider the function g from the set of all non-negative real numbers into itself. And what is g? G is the cube root of the input. If you recall, at one point we defined nth roots of positive real numbers where n is any positive integer. You can extend that slightly to include 0 by defining the nth root of 0 for any positive integer to be 0 itself, so that this function g is well defined. Okay, now this function g has an inverse. As a function of this type with this domain and that same range, it has an inverse, and that inverse is this function. It's the ordinary cube function. Think of this function in place of our f, and this function g then is the inverse of f. Just like f inverse, f is the inverse of g, g is also the inverse of f. Alright, so this is nothing but f inverse. However, the problem here is that although this is differentiable, particularly at 0, the derivative of f at 0 is equal to, in fact, from calculus you know its derivative anywhere in the domain. It is 3x square. You know these formulas. Now the derivative is 0. So the thing here is this. Does the conclusion of the lemma fail? Yes, actually it fails. That's because g is not differentiable at 0. Do not forget that this is not the conclusion of the previous lemma. This is one of the hypotheses failing. We have two things in the hypothesis, right? F needs to be differentiable at x naught, which is true. In this case also it is true, and our x naught is 0. But y naught is also 0. However, f inverse, which is g, is not differentiable at 0. And that is why the conclusion actually does not make any sense in this case. The conclusion also fails because of this becoming 0. So this relation is not true in this case. Okay, so that is one example which shows that things can go wrong. Now, after this, one may be looking at this equation and thinking that, oh, if we use Leibniz notation, which is this, say, if y is equal to fx and x is equal to f inverse of y, then you can write this equation like this. At the appropriate points, that this you are differentiating at y naught, and this you are differentiating at x naught. So it takes on a particularly nice form which is very easy to remember, easier than remembering this. However, as the author has already discussed, these notations are not used in this book because one quickly gets confused with these things, and especially when one works in functions of several variables, there if you use this type of notation, this kind of things, then the confusion is just it goes on increasing, okay, and very soon we forget what we are doing, and you just get trapped in an endless loop of confusion. So we won't be using this type of things here, this type of notation. All right. Now we go towards the main result of this section, which has a name also. It's called the inverse function theorem. In it, we keep that part of the hypothesis intact. Still f is differentiable at x naught. However, this time, instead of assuming that f inverse is differentiable at y naught, we relax the condition and say f inverse is continuous at y naught, and conclude that f inverse is differentiable at y naught. In fact, that's what we were trying to do. We wanted to conclude that f inverse is differentiable from something else, and that something else is the continuity of f inverse at y naught, not differentiability. So let's state the result. Inverse function theorem. Let f from x to y be an invertible function. The beginning is just like before, is an invertible function where x and y are both subsets of R. Again, let x naught be a point in x and y naught be a point in y, such that y naught is equal to f of x naught. Till this, everything is like that lemma. But now comes the change. Let f be differentiable at x naught with, this additional condition must be mentioned here, with the derivative of f at x naught not equal to 0 and let f inverse be continuous at y naught. Okay, then f inverse is also differentiable at y naught. This is a conclusion now, not a hypothesis. Then f inverse is differentiable at y naught, and this part is also same as before. Okay. We want to prove that the derivative of f inverse at y naught is this value. Now this value makes sense right from the very beginning, because we are given that f prime of x naught is non-zero. Now we are going to rewrite this final thing, our aim that we want to prove, using the definition of derivatives. We need to prove that this limit, what does this derivative mean? It means the limit of let me use the scale so that it looks nice. The limit of f inverse of y minus f inverse of y naught divided by y minus y naught. As y approaches y naught and y is varying over the set y naught difference y, this is what this derivative means. We need to show that this is equal to this. And in proving this, we can use the sequential formulation of limits. If we are able to show that for any sequence in this set, y difference y naught converging to y naught, this sequence, that is the sequence of, whose terms are this ratio, where in place of y you would put the terms of that sequence, this sequence converges to this, then that is equivalent to showing that this limit is equal to this. So what I am trying to say here is this. Sequences save us so many times in analysis. Unfortunately, they do not save us as much in topology. In topology, sequences are really pretty useless. There you have to use some other types of objects, nets, filters. Maybe one day we will see what those things are. And sequential formulation of limit rests on proposition 939. So you can go back to that proposition and see what we mean by proposition 939. It's enough to show that this limit exists. f inverse of yn minus f inverse of y naught divided by yn minus y naught is equal to this for any sequence yn in the set y difference y naught converging to y naught. In other words, if we arbitrarily take a sequence yn in this set which is converging to y naught and show that this sequence also is convergent and converges to this, that means this limit is equal to this. And this is happening because of proposition 939. Okay, I am not going to further elaborate how that is the case. You go to the statement of proposition 939, you will realize what we are talking about here. So, let yn be any sequence in y difference y naught that is converging to y naught. Note one more thing, a very small thing. We have carefully decided to start the index n from 1 so that we do not confuse these terms with y naught. Let xn be these real numbers. Now see, each yn is going to be a point in y difference y naught, so ultimately a point in capital Y. So their f inverse images will be some points in capital X because f inverse maps y into X. We are naming them, okay. Let f inverse of yn be called xn. Then xn is a sequence in X. That is easy to understand. However, is it a sequence in X difference X naught? Do not forget that X naught already is something we have chosen. X naught is a point in X at which f is differentiable. Suppose that xn is equal to x naught for some positive integer n. Then f inverse of yn is equal to x naught, or because we are dealing with a bijective function f whose inverse exists, then yn becomes f of x naught. However, f of x naught is y naught, and that contradicts the fact that none of the yns is actually equal to y naught. A contradiction. So that means our supposition is wrong, and so xn is actually a sequence in x difference x naught. But then comes the next question, is x then converging to x naught? Yes. And this is where continuity of f inverse is used. Since f inverse is continuous at y naught by the sequential formulation of continuity. Oh, let us also mention, and yn is a sequence in y, a sequence in y difference y naught, but after all also a sequence in y, converging to y naught. We have this limit of x n equal to limit of x n means f inverse of y n. Because of this continuity, limit can be taken inside. And we know this limit y naught, and that is x naught. So that is why not only is x n a sequence in x difference x naught, but actually it is converging to x naught. And now we are going to again use proposition 939, sequential formulation of limits, but this time with the fact that f is differentiable at x naught. Since f is differentiable at x naught by proposition 939, limit of f of x n minus f of x naught divided by x n minus x naught is equal to f prime of x naught. How? That's because you know that this limit f of x minus f of x naught divided by x minus x naught as x approaches x naught on the set x difference x naught is equal to f prime of x naught. So if you find a sequence in this set converging to x naught, then this should happen by proposition 939. However, now you can manipulate this equation. Limit n tends to infinity. Now note that f of x n actually is nothing but yn, and f of x naught is y naught. Similarly, x n is f inverse of yn, and x naught is f inverse of y naught. This is equal to f prime of x naught. Now you recall part E of the limit laws for sequences from chapter 6. That is, you go to theorem 6.1.19. There you have the algebra of limits. Sum of sequences, product of sequences, they converge to sums of limit, that thing. And apply part E, which says that if you have a sequence of real numbers converging to some limit and all the terms of the sequence are non-zero real numbers and the limit is also non-zero, then you can take reciprocal. You can take reciprocals of all the terms. That sequence will also be convergent to the limit which is the reciprocal of the original limit. And are we dealing with non-zero real numbers here? The denominator of course is non-zero, but the numerator is also non-zero. None of the yns is equal to y0. So we can take reciprocal. One more thing, f prime of x0 is also non-zero. So the limit is also non-zero. So by theorem 6.1.19 part E, we have now if we take reciprocal, then on the left hand side we get this f inverse of yn minus f inverse of y0 divided by yn minus y0. And on the right hand side you reciprocate this. And that's what we wanted to show, because of this fact you can again apply proposition 939 and claim that that original limit is equal to 1 over f prime of x0, and hence the derivative of f inverse at y0 is this. So that's how you have the proof of this result. This result is convenient, I mean it's more powerful than the initial lemma. Let us summarize this briefly. What it says is that you have a function f which is differentiable at x0 and which is also invertible, because otherwise there is no inverse, and f prime of x0 is non-zero. What else is given? F inverse is continuous at y0, which is f of x0. Then f inverse is also differentiable at y0, and that relation, that equation is true. So that equation helps you to calculate derivatives of inverse functions, and that's why it's called the inverse function theorem. We will use it to calculate derivatives of inverse functions of some known functions in the exercises. And the section ends here itself, I mean the theory part. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.